Florentine. I work at the USGS and I am co-lead of the IARPC Glaciers and Sea Level Collaboration Team. Thank you all for coming. My pronouns are she and her, and I'll let Joe and Richard pipe in if they have any other introductory comments here, but I think we're gonna hit the ground running and hand the reins over to Jason Briner from University at Buffalo. He's our first speaker, and as Anne said, we're going to have questions right after Jason's talk, and then we'll shift gears to hearing from Heiko Goelzer, and we're going to ponder this latest science about the Greenland ice sheet, how it is evolving, will continue to evolve, and its contributions to sea level rise. So Joe and Richard, any other opening comments?
So we last had a joint meeting on ISMIP6 back in March of 2019. We had Sophie Nowicki and Alice Bartholden who were describing the experiment and essentially the procedures that were going into it. So now the experiments have been conducted and results have been published. And so we're going to hopefully have an excellent discussion about what the implications of those results are.
Excellent. Thank you for that context. And yeah, I didn't mention or emphasize it, but this is a joint meeting with the modeling sub-team. And so, of course, we're going to have some observations that ground that modeling piece as well. So cutting edge science, thanks all for coming, and we'll hand it over to you, Jason. Thanks for presenting.
You bet. Hi, everybody. Good to see you and good to meet you if I don't know you. Let's see if I can share screen and get this thing going here. So let's just first do a check. Can everybody hear me and see the shared screen?
Yes.
Awesome. Well, I wanted to thank you for having me present this story to you all. And thanks to Joe for inviting me to do this. This is probably the highest level expert audience that one could present this kind of science to. So forgive me if things are either too broad or too narrow for you. I'm trying to do my best given all the knowledge in the crowd here. So I should start by saying that it's just an absolute pleasure to talk about this work. As somebody who's done glacial geology for my career, that's what I do as a specialty. This is the first time I've really worked with such a broad team to be able to use the glacial history records that people like me and my students produce to scale that up to a broader story that I'm going to tell today. I'm the one talking to you now about this, but there's tons of expertise that went into this project, some of which I know very, very little about. So excuse me if I don't know some of the details on some of the modeling or the climate reconstruction that I'll be going over today. In particular, the ice sheet modeler is Josh Couzone, who works with the NASA JPL team on ISSM. And Jessica, so he was mostly a postdoc during this project. And then Jessica Badgley, who's a PhD student at the University of Washington, she did the climate reconstruction work. And it's really those two and then the broader author list that I'm leaning on heavily to. I'm just here telling you what we all did together. Those guys did a lot of the work. So the story starts with this chart that some of you might find familiar. It's, should I be monitoring these chats as we go?
No, we'll keep an eye on it.
Okay, thank you. This is the result from the MB2 Greenland paper that came out last December. And it's a plot showing the rate of mass change of the Greenland ice sheet spanning from the early 1990s up into a couple of years ago. And each vertical bar is 1 year of data, observations, or that allowed a group to determine what the rate of change was of the Greenland ice sheet. And the more colored bars are just the more independent studies, values that go into the average of each one of these data points, each one of these vertical bars. And you can see that generally the ice sheet went from a state that was generally healthy, close.
I think you went on mute.
Sorry, is it?
Fine.
Yeah, so it said the host muted me, but can people hear me now?
Yes.
Thank
Sorry
you.
about that.
Sorry about that. I'm not sure what happened. Anyway, the Greenland Ice Sheet went from a period of about stable condition, more or less stable conditions in the 90s, and then around 2000, it started to lose mass at an increasing rate. And even today, in the last few years, although the rate has climbed back towards zero, it's still a negative rate. So the Greenland Ice Sheet is losing mass. And in particular, the last couple of years have had pretty severe melt seasons. And so the bars of the last couple of years are down, are best estimated to be down where they were in like the 2010 to 2012 window part of this graph. The other main point of me showing you this plot is that we don't have records of this graph. We cannot extend this graph further than what you're looking at here into the past. And this is a relatively narrow view of the mass change rate of the Greenland Ice Sheet. We know, however, that Earth history provides more variability than we can capture in the last 20 years. This is a plot showing a couple of different temperature reconstructions spanning the last 8,000 years from Greenland. These happen to be borehole temperature reconstructions. There are many different ways one can reconstruct temperature during this interval, which is the Holocene, or this is just the middle and late Holocene, really. Holocene spanning the last 12,000 years. And we know that the Holocene experienced a period in the early part that was warmer than today, or as warm as today. And the Holocene also encompasses periods of rapid climate change, both cooling and warming. And if we could understand mass change rates during these past climate swings and temperature states in the Arctic, we might have a better ability to understand where the Greenland Ice Sheet's going in the future. So the work that this group of us worked on, or the question that we wanted to try to answer, was how do today's rates of Greenland Ice Sheet mass change compare to the rates in the past under these different climate situations that I just showed you in the last slide. And this is our project framework. So this was an NSF grant that we got funded that started in 2015. So here we are 5 years later. And the overall framework has these three components. I'm the bottommost one, ice margin reconstructions. That's my main bread and butter. And we wanted to combine that with ice sheet modeling, because it's really only through ice sheet models can we turn the paleo record into something like the mass change rate of the Greenland Ice Sheet. That's not something that paleo observations or paleo data can provide directly. So we wanted to do ice sheet modeling. And then we also wanted to force that ice sheet model with improved paleoclimate reconstruction. And combined, these are the three branches of our project. So I'm going to start with paleoclimate reconstruction. And this is Jessica's work. It came out in a really comprehensive paper this year. And the key here is that this group uses data assimilation techniques combined, which uses climate modeling to basically spread spatially paleoclimate information. So the temperature data all come from ice cores, and the accumulation or the precipitation data also come from ice cores, but it's not just scaled to temperature according to the standard relationships of how precip scales to temperature, which is the norm for paleo ice sheet modeling. They reconstructed precipitation using accumulation records from ice cores. So they basically used all the ice cores on Greenland, all the deep ice cores that span the Holocene, to reconstruct a temperature and precipitation grid across Greenland. And we used that grid to force the ice sheet modeling through a positive degree day model to get surface mass balance. Because there's uncertainty on the temperature and precipitation reconstruction, we decided to use three different temperature reconstructions that are within the range of the uncertainty, and three different precipitation reconstructions that are within the range of uncertainty. You combine the three temperature and the three precipitation reconstructions to get 9 different combinations of temperature and precipitation. And we did, therefore, 9 different ice sheet model simulations. So we generated a surface mass balance grid over our model domain, which I'll talk about in a little bit, using a total of 9 different climate reconstructions. This isn't really a true ensemble because it's so small, but we call it our ensemble anyway. It's only 9. So now I'm going to talk about ice sheet modeling. And this was, being this NSF grant, we also had an outreach component, and we had this wonderful artist who worked with us that drafted up these little like postcards of the students and the younger colleagues that were part of our project. So this is Josh Kuzone. The idea was to turn a scientist into a superhero, to try to empower youth to be interested in doing science. So this is Josh, and he's the master modeler. He's the guy who worked with the ISSM model at JPL. Now, on the left is Greenland, and in the red is our model domain. When we started this project, when we proposed this work in 2014, which was the same year that my oldest son is now, and he's now 6. So that's my time frame for when this all began. And when we started it, the modeling community didn't know how to do calving very well in ice sheet models. Ice-ocean interactions was tough then, it's still tough. Supercomputing power isn't what it is now. And so we decided that we would have the best results if we just modeled about a quarter of the Greenland ice sheet where it's mostly land-based. Our domain does include the very difficult to model Jakobshavn isbrae, but largely this is a land-based piece of the ice sheet where ideally ice-ocean interactions or our inability to model ice interactions wouldn't influence our outcome tremendously. The other point of this slide, which you can see on the right, is based on the 46-year-long record of historic mass change rate that Mougenot et al. Compiled. You can see that this particular domain, which is shown in red, has a very almost one-to-one correlation with what the whole ice sheet does. So even though our results that I'm going to talk to you about today are from this southwest domain, at least in historic times, there's a pretty tight relationship between what happens in that domain happens across the entire ice sheet. Not in magnitude, but in trend anyway. So I'm going to jump right into showing you a movie from one of the 9 simulations that we ran. And oops, just started to go. No, go. So here it is. So this is just surface elevation change in this particular movie, this simulation, with red being high thinning rates and blue being thickening. And the main thing you can see is in the early Holocene, it's quite a bit red. It stops at the pre-industrial time period. So I'll go back and show it just one more time. So we see a lot of red colors in the early Holocene here, some thickening in the middle, in the interior. And then things are starting to look more neutral. It's kind of pink and light blue all the way up until the pre-industrial period. And showing you now cumulative ice mass of all 9 simulations through the Holocene up to the pre-industrial anyway, you can see the spread in cumulative mass ice loss. But generally, before about 7,000 years ago, we're a losing mass situation. And then 7,000 or 6,000 and onward, we're one of sort of gaining. And by the end of the Holocene, we're not changing a whole lot. Maybe some of the models show quite a bit or some growth, some show a bit of leveling off. If we put this in terms of rate of ice mass change, you get this plot, and here again is all 9. Again, showing negative is down now. So this is the last 12,000 years like before the Holocene. You can see a lot of negative mass change rates in the early Holocene, and then a little growth and or neutral ever since the early Holocene. Just one note, we did our modeling. No, we didn't do our modeling, but we extracted the data. We produced mass change rate in terms of units of century. We felt like this was at roughly our capability. So we may not be as confident in a gigaton per year value back in this time interval, whereas we can have higher confidence in the gigaton per century value. So I talked about paleoclimate reconstruction, and then I showed you the ice sheet modeling. Now what we did was we compared the ice sheet modeling with ice margin reconstructions to see if there's any similarities or differences. This is one little part of Southwest Greenland. The ice sheet is on the right, the ocean is on the left. And these squiggly colored lines are moraines that are on the landscape today. And these delimit former ice margin positions. The dashed is where it's a little bit less clear, and the solid is where we're have much higher confidence in where the ice limit was at that time. We needed to then know the ages of these moraines. So we used one of these glacial geologic dating techniques called cosmogenic nuclide exposure dating. This is something that we do in my lab here in Buffalo. We use the isotope beryllium-10 to basically get a date on when a moraine or the boulders on a moraine are deposited. They basically build up an inventory of a cosmogenic isotope on their surface, much like our skin builds up a suntan if we were to sit out in the sun for a long time. And we can use that as a dating method. So here again is the rate of mass change plot. And I'm going to zoom in to this period in the early and into the middle Holocene. And now I've transformed those 9 values into a mean and then a 5 to 95% probability range. And then here is that map of moraines again. And on the bottom are the ages that we got from our dating campaign that spanned the last 5 or so years. And I'm going to plot as vertical bars on this mass change plot, which really only spans 12,000 to about 7,000. Each one of these vertical bars, we know that the ice sheet paused in its overall recession. It paused or re-advanced, indicating that it must not have had a negative mass change rate at the time of moraine formation. It must have approached 0, or maybe was increasing and then decreased again. And that's maybe where you would get a moraine deposited and the ice sheet would continue its march back towards its present configuration. And indeed, if you look at the vertical blue lines, we felt like within error, they all sort of coincided with a peak in, or a transition from negative to positive mass change rate. There's a giant one 8,200 years ago, which is a well-known cold event followed by a big warm period. And that's where we have a moraine formed. It's also of note, the relationship isn't perfect, but these are completely independent approaches to get at Greenland ice sheet stability. The other piece of information here is that, between moraines, like these 2 moraines, if you can see my cursor, the one at 10.5 and the one at like 9.5, we didn't have any moraine deposited on the landscape. There was no moraine that we had identified that dated to that interval. And on our simulated mass change rate curve, that's a prolonged interval of negative mass change values. So we felt like these 2 independent data sets had a certain correspondence that led us to have some trust in the model simulation, the model results. Okay, now this figure is what we published in the paper that came out in October. And again, it's the mean value of the gigaton per century data. And then every single, in this case, it's not a shaded zone, every little tick is one of the 9 simulations. And then in the far right is the summed histogram of every single one of those. So it's all the centuries from 12,000 to the pre-industrial, and then it's all 9 simulations in every single one of those centuries. So that's all the data, and it's compiled in this histogram on the right. So that's where we left it up to 1850. And so now I'm going to talk about what we did with our modeling next. We didn't stop at the Holocene. We wanted to model the ice sheet in the last century and also into the future. And we used climate forcing that's been reconstructed from box. And these are now gigaton per year data, 1850 to 2012, I think. And this is our reconstruction. So you can see negative gigaton per year values in the time in the Arctic when there was a warm period in the 40s. And then again, we're just catching this transition from the 80s and 90s into the 2000s, where we're starting to see a lot of negative mass loss rate of the Greenland ice sheet. And then as part of the ISMIP6 project, and we'll hear about this next, I presume, we used Josh's paleo simulation, and then as the model spin up, and then we ran it forward using the climate forcing as input from CMIP5 and 6. And so there are several of these scenarios which use RCP 8.5, and then there's two in reddish hues here, reddish colors, and there's these two green ones are RCP 2.6 climate forcing scenarios. So what we then did was we sort of averaged all these data you're looking at here into to be gigaton per century rates, so we could splice it onto our master curve from the Holocene. Before I show you that master curve, I just want to come back to this movie. And this time what I'm going to do is I'm going to bring it right up to the current century we're in. And you'll be able to see how red that is compared to the context of what you've seen so far leading up to it. So that's where it ends. That's the current century. And just to zoom in on that a little bit more, these are the warmest 2 centuries in the Holocene on the left panel and the middle panel. In the right is the current century thinning rates from this model run using RCP 2.6 climate forcing. Here's one of those. And then here's one of the RCP 8.5 climate forcings. So you can see both, even the 2.6 and especially the 8.5 forcing look like quite a bit more thinning in this century than in any time in the Holocene. And that was our basic punchline. So here now is putting it all together. I've added this downward line here, and these 2 green circles are the gigaton per century values we get from the 2 RCP 2.6 climate forcing runs, and here are the 8.5 runs. You know, one of the 2.6 runs overlaps this PDF of all the Holocene values, but mostly these are all beyond 99% of all of any gigaton per century value that we got in the entire Holocene. So people have been calling this the hockey stick now. We've had it for temperature, we've had it for CO2, and now we have one of these hockey stick curves for an ice sheet response to those forcings in units of gigaton per century. So basically that's it, and I'm going to stop. And the conclusion here is just that it seems like this century is exceptional in the context of the Holocene. Thank you.
Great. Yes. Thank you, Jason, for the nice comprehensive presentation. We'll open it up to questions, and please feel free to type your questions into the chat. Otherwise, you can unmute yourself, and we'll start a brief discussion, and then we'll make sure we reserve sufficient time to hear from Heiko, of course, too. We'll get Jason out of here so he can teach at the top of the hour.
Can I kick off?
Yes, go for it. Thank you, Jonathan. Go ahead.
Jason, you've stopped sharing your screen, but if you go back to, or you don't have to, but if you look, okay, brilliant. If you go back to the slide where you have the projections of mass loss up to 21, this one, yeah, okay, brilliant. So you're forcing that with, I don't know, yeah, CMIP5, CMIP6, you don't expect those simulations to reproduce any 1 year. You do expect the interannual variability to be, you know, realistic. And I don't know. So 2019, the Greenland Ice Sheet lost 532 gigatons. You draw a line, you know, where 532 goes across there, you're going to hit RCP 8.5 when it first has a mass loss of that at about 2070. That's RCP 8.5. None of the other simulations have a mass loss of that rate. Now I'm going to be like a pedant or like irritant and I'm probably going to ask Heiko exactly the same question because I know what he's going to show. And the reason I'm asking this is because I've just been asked to write a section for the AR6 on exactly this. What I would propose is this kind of implies that the ice sheet model, this ISSM, even forced with RCP 8.5, is just like showing so much lower sensitivity to climate forcing than the observations. Do you want to comment on that? And then, like, at the end of Heiko's, he can comment on that.
Yeah, thanks for the question. I appreciate it. I have two comments, and the first one is that something to keep in mind is that and I didn't write it here in the axis label, but this is only for the southwest quadrant of the ice sheet. So the value you cited was Greenland ice sheet wide, and
Right.
this is just for our model domain.
Okay.
I think, however, if you divided the value you cited at whatever 539 or whatever it was by a half or a third, which not by area, but it seems like that's how our model domain scales to the ice sheet in terms of mass loss proportion. Still, your point is probably still valid, that it's going to be a quite low value that these model simulations don't hit until decades into the future. Yeah. So the first comment is to keep that part in mind. We didn't want to scale to the whole ice sheet because there's not a way to do that with much certainty, it turns out, that we were able to come up with. But it does sort of call in question whether or not RCP 8.5 is really an end member scenario.
Actually,
right?
I disagree. I think it calls into question like the physics in the models, or the initial conditions, or the boundary conditions that you use for initialization of the model. I mean, Heiko's going to talk about this. I think he's going to talk about the ISMIP6, intercomparison. And again, like, not very sensitive to extreme warming. RCP 8.5 over the Arctic is going to be like 9 degrees, 10 degrees by 2100, isn't it? That's hot. That's really hot.
Thank you, Jonathan. That was a good whopper of a first question, but I think it's good for all of us to be thinking along those lines. And we have one more question, I think, for the time being, from Mike McCracken here in the chat. Mike, do you want to unmute yourself and ask that in your own voice?
Okay, so I want to clarify sort of how the model works and understand it. So are you basically just imposing temperature and precip from a GCM, or are you actually treating the forcings that are applicable to the ice sheet? And I ask this because I'm concerned about sometimes using past analogs for the ice sheet. So in the past, orbital variations have a seasonal effect on the forcing. And so you might have a hot summer radiation or whatever. Whereas with CO2 and greenhouse gases, the forcing's occurring all year long. And so the ice sheet doesn't get to really cool in the winter because it still has that positive greenhouse forcing. And so the ice would warm up compared to the past. And so I guess I'm curious how the model is doing that. Is it just imposing temperatures, or is it really also imposing the fluxes that are occurring at the surface?
Thanks for the question. That's a really good one that I don't know the answer to. I do know that as we're currently trying to, we're fundraising and writing a proposal to scale what we've done up to the entire ice sheet. And I read in our current proposal that we want to do a better job at being faithful to the forcing and acknowledging that, Holocene, with the higher amount of insulation, the seasonality you mentioned, the configuration is different. The forcing is different in that early Holocene warm period than the CO2 forcing that we're in and going into now. What I don't know, and what we could find out from Josh, Heiko might know, is that I believe our surface mass balance stems from just the temperature and the precipitation. Using via a PDD model.
Thanks, Jason, and thanks, Mike, for the question. And Meredith made a good point that if Peter and Tim, who indicated they have questions right now, if you want to type those into the chat, you can, and Jason can address those, sort of multitasking as Heiko speaks. And for those uninitiated, PDDs are positive degree days. I don't think we have anybody like that on the call here, but anyhow. All right, so we're gonna now hear a little bit more about ice sheet model. So we'll hand the reins over to Heiko. Definitely plenty of trains of thought to keep going through our minds as we're listening and learning. And again, feel free to use the chat or keep your questions until the end, and we'll have plenty of time for discussion. So Heiko, thanks so much for agreeing to present, and we'll hand over the reins to you.
Okay, thank you very much for inviting me and for the opportunity to present this work here. I'm gonna make an attempt to share the screen. And if you're all happy with this, then I can start. Does that look okay?
Yes.
Can you hear me well? Okay, so yeah, I'm presenting this work which comes from a big international community effort called ISMIP6. And so I want to first of all acknowledge the work of all the people that go in here. ISMIP6 is led by Sophie Nowicki, who has been at NASA before and is now at University of Buffalo, by Tony Payne, who is from Bristol in the UK, and by Eric Larour, who is at the JPL. And there's many, many more people that have contributed to this exercise. So I'm very grateful to all their input. So what I'm talking about today is only the Greenland projections. There's also an Antarctic component to that intercomparison exercise that you will have to do with probably Helen or maybe Sophie at another point. So yeah, so the presentation is really about the ice sheet model intercomparison project for CMIPS6, as it is called. And the goal of this project is to estimate future sea level contributions from the Greenland and Antarctic ice sheets, and along with it, the associated uncertainties due to the climate model forcing, due to uncertainties in the ice sheet simulations. And it was always the goal to provide direct input into the IPCC assessment cycle, so for AR6, which is happening at this moment. ISMIP6 is the first time that ice sheet projections are fully integrated within the CMIP framework, and what I mean by that is that ISMIP6 is an endorsed model intercomparison part of CMIP. Before that, there have also been ice sheet model projections of sea level, but they were not fully included in CMIP in form of this endorsing of the MIP. So I want to start with showing you the experimental framework for ISMIP. And so the general idea was to basically take the climate model output from all models participating in CMIP6 and using that as a forcing for standalone ice sheet models. And this is the part that I will talk about today. So this branch here, basically from the CMIP models to the standalone ice sheet simulations. There's, however, also a component to ISMIP6 which was proposing to work with fully coupled models where the ice sheet component is an integral part of the GCMs. This is something that's kind of under development. There's currently 2 CMIP6 models that have a fully coupled Greenland ice sheet, not Antarctica. And so, but we felt that we needed to advance in that direction and propose some form of comparison in that regard. And the goal, of course, of this fully coupled simulations is to take into account the interaction between changing ice sheets and climate, which is not the case when you go this way here. So I will talk about really this side of the figure here. And one important thing to mention is, although it says here CMIP6, in the course of our project, we had to decide to use CMIP5 model output. The reason for that is that CMIP6 was considerably delayed, and we are always with the ice sheets kind of at the end of the processing chain. So that made it impossible for us to base our main analysis on CMIP results. We have made some CMIP experiments, as you've seen in Jason's talk just before. But the main analysis that I'm showing today is based on CMIP5. So here you can see now specifically for Greenland, the experimental setup that we have worked with. So in the top here, you see the CMIP5 models. Another reason for using CMIP5 is really that at the time we started with these experiments, we could select from the full CMIP ensemble and make a meaningful selection, because we had to limit the amount of experiments so that our ice sheet modelers and also the people producing the forcing data could cope with the work. And so at this moment, we could select CMIP models based on their performance over the historical period. So choose only the best models if you want. And this was based on certain metrics that we thought was important for the ice sheet. So temperature over and around the ice sheet, precipitation and so forth. And then out of these good models, or the better models, we chose a subset of 3 and then 6 models to maximize the spread in the projection, so that we can sample mostly the entire ensemble range of these CMIP5 models. And yeah, with this then, and this is, I think, answering to Mike's question before, the model output from the GCMs is then downscaled with a regional climate model called MAR. And this is necessary because at present the surface mass balance, which is the predominant forcing that we get from the GCMs on the atmospheric side, is not well enough resolved in the GCMs themselves. So we need to process the GCM output with the regional climate model that are forced by the GCMs to produce surface mass balance at the ice sheet surface. And when then taking anomalies of the SMB that comes out of this regional climate model relative to this period 1960-1990, which is typically assumed a period where the ice sheet was in steady state with the climate forcing. And this allows us to impose this SMB forcing for all the ice sheet models, independent of what the initial surface mass balance is during their spin-up and initialization procedure. And you've seen that in the example before. So Josh's model was spun up using SMB, which comes out of a PDD, positive degree model approach. And then from then on in the future, he can use these SMB anomalies on top of that background SMB that he gets from a different model. So that's really the idea. And again, I think answers the question of Mike. Because the ice sheet models are not fully coupled with the climate, we don't take into account any feedbacks dynamically. But one very important feedback is this so-called surface mass balance elevation feedback, where the surface mass balance gets more negative as the elevation decreases. And so we take that into account by parameterizing the effect based on the output from the regional climate model. So on the atmospheric forcing side, that's fairly standard procedure for ice sheet model experiments, ice sheet model forcing. And I think in terms of the quality of the forcing, that's really well justified what is done here. On the ocean forcing side, we have a bit of problem because first off, the ocean forcing that we get out of the GCMs, these models, they are not resolving at all the fjords around Greenland. And so it's not really possible to directly drive an ice sheet model with forcing from these coarse resolution ocean models. Aside from that, it is also a complex interaction that is currently not well understood and certainly not easy to model for a large number of small outlet glaciers around the ice sheet. So we had to rely in this intercomparison, where we want to accommodate all the different ice sheet models, an approach that parameterizes this interaction. So this is arguably a very coarse approach to the problem, but currently we felt the best we could do in terms of accommodating these different models and relying on GCM output. So what we are doing is that we empirically deriving this parameterization based on historical glacier retreat on one hand, and then ocean temperature changes and runoff from the ice sheet on the other hand. These are the two parameters that are expected to be the driving forces for outlet glacier retreat. On one hand, the ocean temperatures may be most obvious, because when the ice sheet, marine ice sheet margin gets in contact with the ocean and gets more heat, and there's something happening, there's like retreat happening. On the other hand, the runoff from the ice sheet is rooted under the outlet glaciers and leads to plumes that rise along the calving fronts and melt the ice there. So that's why runoff from the ice sheet is considered an important driver. In the end, this is combined with the historical retreat, and then we derive outlet glacier retreat that is prescribed in the ice sheet model simulations. And we sampled the uncertainty in this ocean forcing with 3 different scenarios, a median, high, and low scenario for each region. Here I can show you how this forcing looks like from the GCMs, or regional climate models, in the end. So on the left-hand side, you see here the surface mass balance anomaly in gigatons per year as it evolves over the current century. We have 6 different models overall that are run under the RCP 8.5 scenario. And then we have 1 model which runs under the RCP 2.6 scenario. So this is the one up here, which you see stabilizing. How does it look like spatially? You can see here in the middle figure where you have the surface mass balance anomaly from one of these models, from the red model here. You can see that almost everywhere around the ice sheet there's mass loss, anomalous mass loss happening with up to 5 meter additional mass loss at the margin of the ice sheet. And on the right-hand side here, you see an image of these outlet glacier retreats that are projected. So again, you have the 6 different RCP 8.5 driven GCM here. And so you can see that the projected retreat for these different models is overall quite similar, and is going up to, in the medium scenario, these are going up to about 15 kilometers retreat. And then we're sampling this range with the high and low scenarios respectively. So again, here I want to quickly shout out to the participants that contributed with ice sheet simulations. Some of these groups have provided results from several different incarnations of their model, for example, of different resolution or different initialization techniques. So overall, we had 21 different submissions to process. And it's important to note that basically everything that the modelers did before 2015, when our projection starts, is more or less up to them. They're just asked to initialize the ice sheet model as best as they can to the 2015 state. And then from then on, the projections are very guided and prescriptive in the forcings that you're supposed to use and the protocol that you have to apply. But this means that there is a uncertainty which comes out of these projections, which is really the ensemble uncertainty, if you want, of different ice sheet modelers doing different things. Now I'm coming to the results that have been published in this paper, which has recently coming out. If you want to read that, I've also uploaded that to your web system, so you can also find it there. And I'm showing here first the projections out to 2100 for these 6 GCMs under RCP 8.5 forcing and 1 model under RCP 2.6 forcing. And so what you can see in this figure, to just briefly give the numbers, for RCP 2.6, where we only have 1 GCM to represent that, we have 3 centimeters by the end of the century. It looks like this is stabilizing in this particular model. So we only have 1 GCM, so it's far-fetched to conclude on that. But at least we see a very clear difference between the RCP 2.6 scenario and the RCP 8.5 scenario, which is the other curves here. And over these 6 different GCMs, we get a best value of 9 centimeters plus minus 5. And yeah, I want to maybe say a bit more about this uncertainty, which we have been able to compare mostly for this RCP 8.5 scenario, because there we have a larger ensemble of models. There, the ice sheet model uncertainty from these different initialization techniques, different realization and so forth, the range that you see in these color bands here are around 4 centimeters and of similar magnitude as what we get as uncertainty from the climate model forcing, which comes from the spread that we get from the different GCMs. The ocean forcing leads to a numerical uncertainty of about half of that, which doesn't mean that, which is in perspective that I think we have maybe least information, or we didn't do a very physically based job on doing the ocean forcing, but because the SMB forcing is dominant for the Greenland ice sheet, this doesn't translate into a large uncertainty here. So the ocean forcing uncertainty is much lower. I want to also point out some further analysis that we did here per basin and for the different ocean sensitivities. So we have divided the ice sheet into these 6 different basins. Maybe I just want to point out one of them here, which is the southwest that we have heard about earlier today. And you can see, if you remember, that this part of the ice sheet is pretty much land-based. And you can also see that here in the results, because the ocean and the differences in the ocean forcing leads to a very small difference in the total sea level contribution from that sector. It is also the region of the ice sheet which sees the largest sea level contribution, and that again is related to that this region already today has a large ablation area that loses a lot of mass, and this is projected further into the future. So with this, I want to come to a brief summary. The Greenland ice sheet will continue to lose mass until 2100 in all scenarios. So factually, we only have 2, but the other RCPs are between that. We may be able to stabilize the ice sheet for RCP 2.6, but obviously there's more modeling needed to cover the larger range of GCMs, because we only have this one here. Under the RCP 8.5 forcing, the uncertainty due to climate models and ice sheets is of comparable magnitude. And this is what I've tried to point out before, that the largest gap in our knowledge is about the physical understanding and implementation of the carving process, so of the interaction of the ice sheet with the ocean. And before I pass on, and maybe to avoid being slapped by Jonathan, I want to point out 2 shortcomings of our simulations that, I mean, I can also wait for Jonathan's question, but preemptively. These projections being based on CMIP output, of course, here we are only producing results that are forced by that model output, by that GCM output. And it is known that the GCMs have limitations in producing some of the observed changes over Greenland currently. Another shortcoming is that we have not sampled uncertainty from different regional climate models. As you may remember when I spoke about the experimental protocol, we only use one regional climate model, MAR. And although regional climate models agree very well over the historical period, there's recent information that tells us that there may be much larger differences in the future period between different regional climate models, and that's something that we have not sampled here. And finally, I want to add that all of the results that I've shown here are calculated against a control experiment. So the sea level contributions that I'm showing here are relative to this control experiment, which means that by definition, we have removed the background trend of the ice sheet models, and it gives rise to another contribution that has to be found out. So yeah, with this, I want to thank all the people that contributed to this work, from CMIP model evaluation to producing the forcing, and finally to all the ice sheet model results produced by the ice sheet modelers. And I want to thank you for your attention.
Excellent. Thank you, Heiko. And I suppose as we launch into questions, we can all keep in mind just the massive effort that goes into producing these output. And so before we get to sort of collectively challenging ourselves to think about what physical processes, what might be missing, you know, the sort of ways that we can improve these representations. I just wanted to take a second and acknowledge the effort. You know, as Jason spoke to, his son is now 6 years old. And when that effort began, he was much younger. So anyway, kudos to everybody involved in the efforts that have been presented here and the efforts that are ongoing. And with that, I'm actually going to address questions as they've been queued in the chat. So we'll keep it in mind, the points that Heiko mentioned, which are really important in this sort of broad question that Jonathan proposed of, you know, are we even getting the range right? Which is really important for communicating with folks who are making decisions, policymakers and whatnot. But we're gonna first hand it over to Tim Bartholomew. So Tim, if you want to back it up here and ask your question in the chat. It's about this flickering of thickening and thinning from Jason's presentation, seesawing around the modern equilibrium line altitude.
Oh, I'd sort of, could I actually ask, could I shift to Heiko's presentation?
Yeah, you bet.
Okay,
go
great.
for it.
So I was wondering about, well, I guess I had two questions. One of them was very quick though, but so you mentioned at the end about you subtracting the control run from the experiments, and that you suggested that maybe a better estimate of the actual projected sea level rise would add that control back in. And I was wondering, should we in our minds be adding the control run to these experiments? And if so, how much of an impact is that?
Yeah, that's a good question. First, maybe I have to clarify that in our experimental design, we did not emphasize for the ice sheet modelers to be able to produce a historical run matching up with the, for instance, IMBI results that we've seen earlier. And so we recognize that now as a real problem, but at the time when we started this effort, it didn't seem like that's something we could impose. So we're kind of sitting there and we're not happy with it, but that's what it is for now. So if you want to add in the trend, I think there's some possible cases that could be considered. One is work that's already a couple of years old by Stephen Price, where they produced like a committed sea level projections from looking into Outlet Glacier forced to retreat. And from this, you come to a committed sea level contribution of around 6 millimeter extra. So it's really not a lot that is added there. And by the way, these numbers are confirmed by a few models that have run ISMIP6 with a kind of meaningful or better matched historical simulation, also from other experiments that I think are being published now by Isabel Nias. So there is some evidence that this background trend should come out somewhere around 6 millimeter plus minus 5, I don't know. But yeah, we cannot really give that number from ISMIP6, so it has to be found somewhere else.
Okay, so you think that the best numbers from ISMIP6 are as you've reported just now and in your paper of experiment minus control? Yeah, I think so. That's what we should use or think about.
And then you have to think about what background you want to add. That's the difficult part, and that's the difficult part.
Okay, all right. I have a more fun question too, but I should leave that for later.
Okay, thanks.
Yeah.
We have a question from Peter who put one into the chat, but I'll defer to you, Peter, if you want to ask your recent question or the question from before, but take it away.
No, so it was for Heiko, and I guess it follows on a little bit from John, and so I guess you've sort of clarified some of the issues with the RCP 8.5 in terms of you run with the GCM model output that you have. So I guess it's then how do we then make the extreme projections perhaps more realistic? Because at the moment we're already tracking, I think there was a paper recently by perhaps Anna Hogg and Slater, but showing that already in terms of Greenland, we're tracking at the highest 8.5. So you might think that we're already tracking at that, so that might be kind of moderate projection. So it's almost like if we're putting these scenarios together, and this is currently the most extreme one, when in fact we're already tracking at it, how do we get across to not just to the community, that policymakers, that perhaps even our current best state estimate is actually already at the lower end of what we're already seeing. So I recognise that you've already said it's because you've run with the models that you're being provided, but if we kind of know that they're wrong, it's almost like we're offering out a far more optimistic message. We've already hit 1 millimeter a year on a couple of occasions, and CO2 is meant to be carrying on going up, and yet we're sort of offering much lower estimates, it seems.
Yeah, I think that's a very good and very hard question. I mean, I think for me, there's basically two components to this. One is, whatever the climate forcing does, if we stick to this protocol of using CMIP output at all, then this is something to work on. And I think it's not clear whether the recent trends that we see are persistent, because it has been shown by different people, Hannah and also Fedwise, that these recent warmings that we've seen is really related to circulation changes like Greenland blocking and maybe changes in the NAO. And so it's not clear that this will persist. So I think this is something that has to be shown, that this is something that will last and be locked in some way to maintain these kind of abnormous or specific conditions over Greenland. The other part is then on the ice sheet side. I think by now there's a couple of ideas around how we could initialize ice sheet models and bring them to a state in 2015 or whenever the next projections will start, and that they have a better representation of the observed trends. And that, I think, would help to gain confidence, even if I think that this will not make a huge difference on the number side. But that's my let's say personal opinion at this moment, anyway.
Great, thank you. Cheers.
We are approaching the top of the hour, so if people have other commitments they need to scoot off to, feel free. But I think this is really fruitful conversation. And one thing I wanted to draw attention to, I actually put onto the event page, but Twyla Moon and others on the search committee recently published a paper about communicating sea level rise projection results to policymakers. And I think that that is a really useful synthesis of some helpful guiding principles that they've gleaned from their efforts in that realm. And certainly this is something we can all continue to think really critically about, not just how the results are communicated, but how all the sort of scientific nuance and caveats and known shortcomings and deficiencies are conveyed as sort of but still can be applied. So it is a challenge, and these are all really good questions. So we've got several questions in the chat, and I think we've had a couple people already leave to go to their other commitments. Let's see here. I guess.
Can you just quickly say, if somebody feels like he wants or she wants to get the question answered and it's not happening now, and you feel free to contact me by email.
Excellent. Thank you, Heiko. Thank you for that willingness. And so we have a couple of responses. I'd also like to point out that you can actually save the chat. So maybe we've got a long series of questions from Mike McCracken, who I think has already left, about surface energy balance representation in the model and also cowling representation. So I think, yeah, pursuing that via email is probably a good approach.
The one point I would make is,
go for it.
Would be a suggestion that now that you actually have coupled models, even if there's just two of them, it would be very interesting, it seems to me, to check the approach that you're using for going with these uncoupled models and see if that is working when you have coupled models. I mean, when we coupled atmosphere and ocean, there were real problems because of the coupling and how we had to do it, and things got missed, and there were trends and a whole bunch of things. And so coupling makes a lot of difference, because I guess I'm wondering if you're bringing over from the GCMs the flux into and out of the ice sheet that they are calculating or must be calculating to get the temperatures. And so it would be an interesting comparison to do, and you now seem to have the potential capability to look at that.
Yeah, thanks for the suggestions. That was actually the original plan, to run really the two branches, like to run the same standalone model that is also in the coupled model, and to really be able to fully compare the two. And this is something we'll pick up on in the next iteration. I hope when there's more models participating. That's a very good suggestion.
Go for it, Tim.
So I've got another question if there's time for that. So this is obviously a phenomenal effort of collaboration and many different, many different modeling groups. I understand that this was all accomplished with essentially like very little funding for any of the modeling groups that participated. So seeing as this is a sort of federal interagency working group, I definitely would like to kind of put my little 2 cents in the hat for more funding for this, like actually explicit funding for these kinds of efforts going forward. And so with that in mind, if there's more funding, and I know that you just completed these studies, but I'm wondering if you've had an opportunity to think about, like, well, what are the next steps? Like, what would an ISMIP7 look like? What do you think are the next really, big targets for this kind of community intercomparison effort?
Yeah, I can fill you in a little bit about this. So first of all, we are still considering ISMIP6 to continue. I think at least until the report is out, we kind of think that we should go on. And there's some, what we think of low-hanging fruit, still a lot of data that we haven't analyzed in detail, a lot of experiments that can still be looked into. Then we are thinking about doing some experiments that are easy to do for the modelers, without additional effort in setting up their models. Like one thing is, for instance, to prolong the experiments for another 100 years in some schematic way, probably, which could be done basically with what is there available. Yeah, then there's some ideas around to kind of continue basically ISMIP6 for a while. And then ISMIP7, of course, we think about ISMIP7, but I kind of like the idea that we stop ISMIP6 and then really think about what is the next turn. And so I will not spoil any ideas of what's going on there, but we definitely plan to do ISMIP7 eventually.
Great, thanks.
Jonathan, go for it.
Oh, hi. Yeah. Yeah, it's a bit. It goes back a few questions actually. It's kind of Pete's question, but framed in a slightly different way. I mean, you mentioned some limitations of the approach, but they were really related to the fact that you're using single RCM, and you didn't think that CMIP5 was that great. But actually, what about things that aren't so great in the ice sheet models themselves? Are there things that you think you need to work on, that particular processes that aren't there, or sensitivities that aren't quite right? Or, is there a next step that the communities could work on for the ice sheets? And like, just to condition that question, and I entirely accept that like one sparrow doesn't make a summer. So, like just the 2019 or whatever. But if you take the mass trends for the last decade, 2011 to 2020, that's pretty close to 1 millimeter a year. That's what you get for the whole century under RCP 8.5. You get actually 90 millimeters for the century, right? So we're not 2019 on its own was 1.5 millimeters. So we're already seeing a rate that's above your worst case scenario. So do you think, I mean, okay, that it might be CMIP5, but actually, it's hot. It does get hot. So do you think there are things in the ice sheet models that need to be addressed?
Yeah, so actually I didn't mention that the difference between CMIP5 and CMIP6. So it's true that in fact there are a few CMIP6 experiments that we have run, and the ones that we did run, this could be coincidence because we basically took the models off the mill as they came out. We kind of processed them and ran some experiments. So this doesn't say anything specifically about the CMIP6 range at this moment, but so they all came out mostly higher than the CMIP5 runs. But to your other question, ice sheet model. So one thing that I like and dislike about ISMIP6 at the same time is that basically every modeler participates with whatever they have. So we did not, take out models that we think are not good or something like this. Which means, in a positive sense, that I think there's a fair amount of different approaches represented, and also in a way, this not asking people to match the historical in a way plays to some extent in our favor, because it means that people did not try to fudge something together that it looks good. So I think in this ensemble of opportunity that we're dealing with, we have a quite range of uncertainty in the ice sheet models that if you would select the best model and only run that, you wouldn't really have. So I think that this is useful, that we have a broader range of uncertainty from the ice sheet models.
Doesn't really address the question, is there something missing? Like I'm not Mickey, but Mickey for Greenland, say.
Yeah, so the elephant in the room is of course the ocean forcing, because this is like very crudely done, and it's not physically based. I mean, it's a schematic approach, empirically driven. So I mean, I like what we did for what it is, but I think to get credibility to the models, we have to do something physically based, and that's a hard one because of the resolution issue on the ocean side, on the whole process. So I think this is the first thing that I would like to see improved in the models, and that comes also on the modeling, on the ice sheet modeling side, with a need for higher resolutions, resolving the outlet glaciers individually, and using the really amazing bathymetry data that is out now. So all of that is not fully represented in ISMIP6. So I think there's a lot of that can be done there.
So just to piggyback off of that, and this is a question to pose not just to Heiko, but maybe to everybody, where are we at with incorporating those process-based pieces into these bigger model efforts? Because it seems like these bigger model efforts are always operating under time constraints, resource constraints, as Tim justly spoke to. And so I'm remembering Liz Olty, who's a postdoc at MIT who works on glacier calving and has a process-based model, followed up after one of these IARPIC conversations, and we had a brief email exchange, and there was sort of a consensus that it isn't always easy and straightforward to take those innovations from investigator-driven efforts and incorporate them into these sort of big, high inertia efforts like ISMIP6. So yeah, Fiamma put comment in here, so I don't know if you want to comment on that, or we can open that up briefly. But that's something that I've pondered.
A little bit, I can comment. Thanks, Heiko. That was a great summary of ISMIP6. You know, I think it's fair to say that when we first started discussing how to provide ocean forcing, let's talk about Greenland now. We knew we didn't really know how to do it, and we debated for a long time, at least the ocean working group that ended up formulating the parametrization as to whether it should even be done. And that's because in every direction, both on the GCM side, so the ocean model, the atmosphere model, and then on the ice sheet side, there were shortcomings and we didn't know how to do it. So from my perspective, this is my personal view, we should see this as a gigantic step forward in the science, but not necessarily in the projections, because I do think there are still processes that are missing, like Heiko said, and I think Jonathan and others are hinting at, that should make these projections suspicious. And so the balance here is between not putting ISMIP6 down, because I do think it's a huge progress scientifically, while being cautious about the projections with the understanding that there's some physics we still aren't able to incorporate. And so, you know, to some of the criticisms that have come, as well as the praise, I think that it's a question of communication of what's in there and so on, from which I think is really important to keep in mind in any commentary on these results in both directions. And on the ocean side, you know, talking about the processes, I think there are some major things we're still figuring out on melting. It's spatial variability, it's temporal variability. I think there's some really new exciting results coming out of studies in Alaska or in Greenland, and some of you I know are involved, and they are questioning some of our, even the highest resolution parameterizations that we're using. And so this is, I think this is on the ocean side, and we don't quite know from an oceanographer's perspective. I think we're still struggling about what even a high resolution glacier model would need as a ocean forcing, right? The one we did for ISMIP was necessarily averaged. Some of the ISMIP models don't resolve individual outlet glaciers, right? So they're averaged over larger spatial scales. But even once we zoom in onto a single glacier, I think the studies that are emerging are ones of extreme spatial heterogeneity in the processes, in the interaction between glaciers and ocean. And so I do think we need to resolve that. Do we need that kind of information and resolution to get things right? And calving for Greenland seems to be the big elephant in the room, and many of the ISMIP models did not resolve it. And how the ocean influences calving, whether the melange plays a role, I think are still open questions, and they're not really in these parametrizations yet. The retreat parametrization was designed to overcome a shortcoming of some of the ice sheet models that did not have calving parametrization. So you don't expect the ocean to be doing this retreat forcing, but we had to bulk it all together. We also had a parallel forcing, which was intended for the high resolution models, which, you know, you don't have to use a retreat parametrization. You could have used the variability in ocean temperatures and ocean and runoff to force your model with your own melt parametrization. But even for these models, I would argue, because we don't fully understand the link between calving and melting, that's hard to do. So I think we're converging, but I don't think we're there yet.
I fully agree, Fiamma, with what you say. Maybe just to fill in is one information. So the models that did use this direct physical approach, the high resolution models that could do it, they all came out lower than the projections that we did with the retreat parameterization. So it's not a significant ensemble. I think there's 3 models that did that. But those ones came out on the lower end. I mean, not the extreme low, but lower than the corresponding retreat parameterization. But yeah, I agree that doesn't mean that we did the best we could on that end.
No, I think you did the best you could. I just think we're not quite there yet. We don't quite know how it works yet.
Another parameterization that we haven't given as much airtime to in our conversation here is the runoff as a function of elevation. So the elevation feedback. And that's another thing that I know our research group at USGS certainly is thinking really deeply about, is how exactly surface meltwater infiltrates into the underlying firn. And I know there are other groups working on that for the Greenland Ice Sheet as well. So it's good because we all have jobs, but maybe we need to continue to inch the needle forward. So Richard, do you have any comments? We're 20 minutes past the hour now, but this has been really fruitful conversation, and I really appreciate everybody's attendance, participation, and input.
Yeah, I think we should wrap up. We've gone a little bit long. I guess I just wanted to say, with regards to the presentations, I'm very grateful for both of the speakers for their presentations. I was thinking about the arc of CMIP and how initially a broad net was cast by Bob Sess in the early 90s to get every GCM that was out there. And then it went through like a policing, like some models were using the wrong gravity constant and things like that. And then there was I think the program managers began to back individual models. And so there was kind of a reduction in the number of models as the models became more and more complex. And so I would suggest that, there, as Fiamma said, there are several outstanding questions associated with the physics involved here. So I don't think we're to a constraint point yet, but certainly it seems like this would be a good opportunity to review, which models are doing things, are having some issues or differ from, other models, and understanding, what those differences are. So it just seemed to me that we're at that point in CMIP. I don't know if Heiko would like to comment on that.
You really meant that on the CMIP side, not on the ice sheet model side, right? If I understood that well.
That's right. I was comparing, the development of the GCMs to the development of the ice sheet models.
Yeah, I mean, I don't have a very good overview of CMIP on the GCM side, and I wouldn't be able to judge if there's models that should be included or excluded. I kind of, in ISMIP6, we very much lean on this philosophy of inclusion, if you want, this idea that, come as you are and not make it hard for people to participate. That's kind of what I have in the back of my head, but I know at the same time that in CMIP they are thinking about quality controlling, or so I think that's probably going in the right direction, and it doesn't have to be exclusive. Like it can just mean like putting the possibility out there to judge the models in a different way, and this is what we've been trying to do in ISMIP. To not exclude any models, but to give some context information, some metrics that tell what is the background drift of these models, how large are they in balance, and this kind of stuff, to make it possible to judge it rather than excluding them right away. So for me, in ISMIP6, that seems like the right approach.
Okay, I think that's it from me, Caitlin.
Great. Well, thank you, Richard. And thank you again, Heiko. And Jason's already taken off, but thanks all. This was really excellent. And please keep up the good work and take care. And thanks, Meredith and Anne, for making this possible. Really appreciate this platform. It's so helpful. So
thanks.
All right.
And the meeting is recorded, so we'll be posting that on the website.
Excellent. Thanks, Meredith.